All right. All right, now people are coming in. Ozzy here? Johnny, Mo, Brandon's here. Justin, Oren, Waldo just joined. Dan's here. Andrew's here. Alan's here. I think we're just missing Ozzy. Oh, there he is. All right. Okay, I think everyone's here. All right. What's up, guys? So welcome to lecture 3. Once again, if you're able to turn your camera on, please turn your camera on for, just as, do it just so like you get used to, having the camera on during school. So I really don't see why you guys like don't like to have it on. I'm like, unless if you have like something embarrassing in your background, or you're in a spot that you can't be in, please have it on. Get engaged, be a part of this class. All right. First and foremost, I'm gonna go through the like more logistical stuff. Hopefully you guys are good. It seems like our roster is becoming like our roster for this class. We got, like one, maybe 2 people trying to drop or so. So we're trying to still figure that out. We're still also trying to figure out the Zoom thing. Just
Are
be
you
on the lookout.
Are you a professor at Rutgers, by the way? Like, do you teach Calc 2 at Rutgers?
No, I don't.
Oh,
All right. If you don't mind, could you just like wait for
okay, sorry.
with the question? Because I'm on a train of thought and I lose it very easily. So just be on the lookout on Canvas, be on the lookout for the GroupMe. It's really weird because like this is like the first year where like the GroupMe isn't as like poppin' as it usually is. Like people, like you guys are very quiet on the GroupMe, feel free to like shoot questions that you have or whatever, like, or anything like that. It's like it's like dead on, I don't know why. Like it's like a resource that you guys should be using. Speaking of resources, I'm holding office hours today, and I think I have one person coming. So if you also want to come, please let me know, give me a heads up, and I'll shoot you the Zoom link. It's going to be probably my personal room, and if it takes more than 40 minutes, then I guess I'll get kicked out and just remake it or something like that. Please ask for extra help. You guys should be going to those tutoring sessions, hopefully, and asking questions, hopefully. I hope it's not like you guys just pop in and then just like leave right after. It's really, really hard, especially if you haven't done this stuff before. It's really, really hard to do this stuff on your own, and it's also really, really easy combined with that to let your pride kind of take over and be like, I can do this, I can handle this, right? So please ask for that extra help. That's like what you should be doing. All right, coming to office hours and things like that. And then lastly, the supplemental videos. I know you guys aren't watching them. I know more than half of you didn't watch the second one, which is gonna be tough because like you're supposed to be watching these videos like before you get to lecture. It's not like I'll save them for later. You shouldn't be pushing them off till later. So please, if you haven't watched these videos, take the time tonight to do them, catch up. I don't think, if I do everything right today, I don't think there will be a supplemental video for this lecture 3. So like, think of it as a reprieve, but also as a time for you to catch up on those videos if you still haven't watched them yet. Okay, like write it down in your notes or whatever. I know you guys and your attention spans are super low, so please like do it. Like set an alarm for yourself or something like that right now if you want to. I don't care. All right, please watch those videos because I want to answer any questions that like, you guys know I'm gonna ask the question, do you guys have any questions like from any of the stuff we've done so far? And if you haven't watched the video yet, then you can't ask any questions from it, right? So please make sure you watch those videos. They're very important. Adlin, what's up, man? You asked if I was a professor at Rutgers. I am not. I don't have a doctorate, unfortunately. So
and I was gonna ask, what time is the office hours?
Oh shoot, 3:50, I think. Yeah, I think it's 3:50. 3:50? 3:50 to 4:50, yep. But once again, these office hours are not just pop in. They're available today because someone asked me for them. So I will be available at that time. If you want the link, just shoot me an email, send me a message on GroupMe, whatever. Anyone else have questions?
So are you a high school teacher?
Yeah.
Okay. Because like you definitely have like lecturing ability. Like
okay.
Like it's not
a compliment.
Yeah, well, yeah.
Oh, okay. All right.
Like
Thank
It's,
you. I guess.
I just figured you like, this is at least something you do.
Oh, I would love to teach at Rutgers, but yeah, I don't think I have the time, and two, I'm probably not qualified for it. Um, although I know they are hiring like postbats now over professors because professors are too expensive, but whatever, that's a whole other thing in itself. Any other questions? No. Great. Then I am just gonna jump right into the sharing. All right. It's recording. We're hot. Yeah. All right. Here we go. All right. All right. So we went through that logistical stuff to start with. Also more logistical stuff. Homework 2, it's due next Tuesday. All right. Just a reminder, there's no class on Monday for the holiday. So please make sure you guys are also staying on top of your homeworks. It's the end of week 1, guys. We're a quarter of the way through. I don't know if that's hit any of you yet. Do you guys realize that or no? Or you're just like, whatever, it's just another week. We're a quarter of the way through. Like there's only like 9 more lectures left, which is crazy. This is gonna fly by. And if you don't stay on top of your stuff, especially your homework and assignments, you're gonna get overwhelmed really, 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 really easily. All right. So please, please, please be on the lookout. That's why I do this at the start of every lecture, to just remind you guys, like homework is due, like when the homework's due, when the next quiz is coming up and stuff like that. All right. Then speaking of which, the next quiz is next Thursday. It's going to cover everything from lecture 1 to 4, including the supplementary videos. So yes, please don't wait till Wednesday night to watch those videos and then like ask me the questions like Thursday like morning. I'm just gonna ignore you. I'm gonna leave you on red. All right. Any questions or issues or anything about the homeworks, about who is this? Is this one of the counselors? I'm gonna assume it's one of the counselors. All right, yeah, I'm gonna assume they're one of the counselors. All right. Any other questions or anything like that for me about the homework? How's the homework going? We are 1 in, so are they okay? Anyone overwhelmed? Anyone like?
Some of the problems were a bit confusing, but it wasn't completely terrible, I guess.
Okay, so thank you for saying that, Waldo. Like I would say, if they are confusing, right? Like the worst thing you could do for yourself is just sit there and stew and just be like, oh man, I don't know how to do this. That's like the worst thing you could do for yourself. Please, like you don't have to like say it in the main chat. Like the point of group me is you can also like direct message me as well. Like, hey John, like, and just like snap a picture of the problem, and be like, how do I do this? Or like, what is this one asking? Or anything like that. Like it takes like 2 seconds, really. So please like ask questions if you have them. All right.
Yeah, I mean, like I asked for help in tutoring, which
Oh,
kind of made it a bit easier, but
but
yeah, I will.
yeah, sorry. I meant to, yes, I also meant to include, yeah, go to ask the questions during tutoring too, if you're not already. But like I said, the worst thing you could do for yourself is just sit there and just be like, maybe I'll get it later, you know, like that's not how you should be doing these things. All right. Today, oh, any other questions, issues, comments, concerns? No. You guys ready? Are you guys ready for today? I know it's Friday. You guys are like gearing for this weekend. Just push through for like another couple hours and you're out of here. All right. So, all right. So for today, I guess Gina didn't talk about the tabular method. She talked about integration by parts, like where you might have to do it a couple times, but tabular method is like a very, very special case of integration by parts that I also want you guys to know how to do because it's like really, really fast and you guys will probably like this one. So I'm going to go through that real quick. We're going to kind of recap the methods that we've talked about so far and the methods that you should know so far, along with the ones from the videos. I'm not going to go through them because once again, you should be watching the videos. And then after that, we're going to talk about yet another method called partial fractions. That's 7.5. And 7.7 isn't really a method. It's more of like a scenario, a very specific scenario, but we got to talk about improper integrals as well. All right. So how should we do this? I think we should just start with just talking about the tabular method. Yeah. So we're still we're still on chapter 7. We're talking about integration by parts, but it's like a very particular case. I don't know if you guys remember from last lecture. There were two like special cases that I said that we were going to go through. One of them being tabular method, and the other one being the grit method, or like the repeated use of whatever. That one was in the video, right? So we're just going to talk about the tabular method. Please check out the grit method if you don't, if you haven't done so already. Where am I? There we go. Nope. Okay, sorry. So I'm pulling up an example here. I don't have an example. Great. All right. So with the example that Gina did in recitation, I think she did something like this. If I'm not, I don't know if you guys can confirm or deny that. I don't know. But basically, what you saw in this one was you had to do integration. IBP is it's the shorthand for integration by parts. If you guys haven't picked up on it yet, but you have to do integration by parts like 2 times. I think, right? I think it's 2 times, right? And the reason for this is because if you notice, one of the functions, it's a power function, right? Do you guys remember LePet? My pet? Yes, LePet. Well, if one of your functions is a power function and the other one is a like an ET, like either an exponential or a trig, you can actually use a shortcut. It's called tabular method. And basically it uses this idea that we are eventually going to reduce down this power function into like just 1. If you think about it, if you remember, if you look at your notes from the recitation, right? It started with x squared. When we did it once, it then became x. And then when we did it a second time, it became just 1. And all that was left over was like a trig function. You guys know what I'm talking about? Those of you that were paying attention to recitation, hopefully you guys know what I'm talking about. So what this means is, instead of doing the full integration by parts method twice, because it takes a little bit of time, right? Because you gotta choose your U and your DV and then integrate and divide and blah, 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 blah. Instead of doing that, you can actually use something called the tabular method, where you kind of create a table. That's why it's called the tabular method, right? It's you can create a table. You can create a table of U's and a table for your DVs. Because if you think about it, you're going to have to choose a U and a DV on each iteration of IBP, right? So the first iteration you choose is x squared for U, cosine x for DV, right? By the way, can someone help me out here? What was the answer when you did this? I don't remember. Was this the problem or no?
It was. I don't think I'm not sure about everyone else, but like she kind of like rushed the end, so like, and then she erased it really quickly, so some of us didn't get to finish copy it down. But I don't know if anyone else has it still.
No, yeah, I have it. The answer is x squared sine x plus 2x cosine x minus 2 sine x plus c.
Okay. Waldo, thank you so much for saying that. You got to let her know. You got to let her know not to erase it right away or anything like that. Just be like, wait, hold on, right? Because that's, yeah. But also, I guess at the same time, she does post the notes on.
Yeah, that's what she did. She was like, "Oh, I posted notes, so you can go back and copy them later."
Right. All right. Yeah. So, but at the same time, it is also good for you guys to be able to like see the process, like the problem being done. You know what I mean? It's different from like just looking at an already completed set of notes and just being like, wait, because then you're gonna be like, wait, how did she get from here to here? You know what I mean? So please, if you missed something, like you gotta please say something, okay? I'm assuming she was rushing to because she probably had a lot to get through. But yes, okay. So this was the answer, right? So let's see how tabular method works. Ready? So there's 2 columns. One where you're going to derive down, the other one you're going to integrate down. Because think about it, right? The DVs always get integrated. The U's always get derived. Yes? Did I lose anyone on that?
Yeah, that's right. Yeah.
So basically, how do we know how many times to derive the red column? Well, you derive it until you get bagel, right? It's a power function. So eventually it's going to go down to 0. All right. So if I derive this, I get 2x. If I derive this again, I get 2. If I derive it again, I get 0. And I stop there because that the derivative of 0 is always going to be 0, right? So for this one, there's going to be 4 rows. Do you guys see how I did that? Yeah, makes sense. This is going to determine how many times you have to integrate the second column, right? So the right column, I have to integrate. So what's the integral of cosine? Oops.
Sine.
Yeah, all right. So you guys are getting your derivative and integral chops back, hopefully, right? I'm glad no one said negative sign. And then what's the integral of sine?
Negative
Cosine.
cosine.
Negative cosine x, good. And then the integral of negative cosine is?
Negative sign.
Negative
Negative
sine
sign.
x. All right, cool. So that's pretty much like the setup for the tabular method. Now let's get to our answer. How do we get to our answer? Some teachers call this the Zorro method. I don't know. Do you guys know Zorro? Do you guys know that reference? I don't know. Some people actually, that might be like beyond your, never mind. Anyway.
I know Zorro.
Oh, you do?
Yeah,
Wait, who was that?
Jeremy. The
Oh.
movie, right? You talking about the movie?
Yeah, the movie. Yeah.
Yeah.
The Spaniard hero who wears the mask and has the fencing thingy, the sword, right? And he moves in a Z motion. So basically, like they call this the Zorro method also because you actually move in a zigzag motion. You start from the first term, you go across down. Then you zigzag back to the 2x, and then you go back down and across. So it's kind of like making a Z. I don't know if you guys see that, right? And so on and so forth until you get to your final row. And what you do is you look at the products of each of these, and essentially you're building your answer, right? So it's x squared times sine x, 2x times this one, and then 2 times this one, right? So you guys see which ones I'm looking at, right? There is one last thing you have to watch out for when doing integration by parts. Do you guys remember the formula yet for integration by parts? What's the formula, the general formula for integration by parts? Remember there was a
Ultraviolet minus voodoo.
Yeah, there he is. Yeah, ultraviolet minus integral of voodoo, right? What this means is that second term is gonna get flipped because of that minus sign. You guys see that, right? So what this does is it's gonna actually cause from term to term, it's gonna cause the sign to alternate. And it always starts on positive. So that's the only thing you need to worry about. So this means your first term is going to be a positive x squared times sine x. So your first term, like you're kind of putting all this together and you're getting x squared times sine x. And look at that, it matches up with that first term in our answer. You see that, right? The next term, it's going to flip the sign because of that minus voodoo, right? So the next term is going to be the opposite of whatever it actually is. So you have to consider any signs that are already in play, you know? So for this next one, it's going to be, I have a yellow. It's going to be 2x. Oh, wait, no, it's negative 2x. Oh, wait, it's positive 2x with a cosine x. Do you guys see how that happened? Right? So it's going to be a positive 2x times a cosine x. Does that line up with the answer we have? Oh, snap. It does. And then the last one, right? It's going to be a 2 times a negative sine x, but this one is going to flip again. So it's going to have a positive. So putting it all together, it looks like a negative 2 times sine x. So it'll be minus 2 sine x, and you can't forget about a plus c. And that's it. That's the tabular method. It's really, really fast, right? Do we have any questions on how the tabular method works?
So this is only possible when
Could you go over why that works again?
Sorry, wait. Yeah, Adlin, I will. Mo, can you say your question again? I didn't.
I said it's only possible when you use exponent or trig.
Oh my gosh, yeah, Mo, what a great point. This is why I said it's a very special case. This only works, maybe I should make it up here. Only works only for when u is a p, like a power function, right? It has to go down to 0. Otherwise you can't do this, right? And then dv is like either an e or a t. So it's a very, very specific case, if that makes sense, right? Because think about it. If your u function wasn't wasn't a power function, right? If it was instead like a trig function or something like that, you would be deriving forever and ever and ever. It would never go away. None of the other, I guess, letters kind of go away either. You know what I mean? So yeah, tabular method, it is a very specific case, but it's one of those where like if you see it, you should actually absolutely do it to save yourself some time.
So can u and dv both be exponents? Because you said power for u and then e, which is the
Well,
exponent for dv.
If they're both powers, then wouldn't you just use like the power rule,
Yeah, that makes sense.
right?
Yeah.
Yeah, don't want to do more work than you need to, right? So yeah. You almost got me though. I was like, wait. Yeah, I'm sorry, Adlin, what was your thing?
I was just asking, like, could you go over it again, like why this works?
Why this, like what part of, because I kind of went through a lot here.
Why the flipping signs and then just tracking the u down to 0 and then flipping signs for the dv. Why that relates to the answer. Like, because like it looks like you're using a little trick here. But I'm not following like why that trick makes sense to use. Does that make sense?
That's what I'm saying. Like I kind of already explained it all. So in normal integration by parts, right? We choose a u and a dv, right? Do you remember that from the formula? So normally like a u would be x squared because Lipet, right? And then du would be 2x, then dv would be cosine x, and v would be sine x dx, right? And normally you would do all this, you would get to the next line and see that you would have to do integration by parts again, right? And then after you do it a second time, you get to like this final answer, right? And if you see with higher powers, like let's say instead of x squared, if this was like an x to the 4th, that would mean you would have to do this 4 times. And that's like a lot of work, right? It's a lot of scratch work you have to do just to get to the final answer. So that's what the purpose of this this technique is for. It's just to kind of like shorten everything. The reason why it works is it's essentially we are doing what we usually do with integration by parts the long way, but it's just you're kind of shortening it because you know that the power function, like I said, the power function will eventually go to 0, right? And if it eventually goes to 0, there will be one term, this one of these terms with just a cosine or just a sine or some form of trig or an exponential that we can integrate. So no matter what, so long as, and that's why we were kind of harping on this before, right? As long as one of them is the power and the other one is an exponential or trig, like this should always work. Maybe if we do another quick example, maybe it'll help. So let's look at one more. I'll call this example 2. Integral of x cubed e to the negative 4x. So I'm looking at this thing, right? Initial thoughts, I can't use u sub, right? Like obviously you guys know it's an integration by parts one because like we're doing integration by parts, but like let's say this was like kind of like a dry run and like we gave it to you or I gave this to you as a problem and you're like looking at this and you're like, what should I do? These should be the thoughts going through your heads. Ready? Can I use u sub on it? And why not?
You can, because
Because you can't, because why?
4x out and to the derivative of that term, you won't get x in the third.
Yeah. So the first question you ask is, can I use u sub? Actually, that shouldn't be the first question. The first question should be like, can I use any of the basic rules? But let's assume you guys did that already, right? Because it looks a little more complicated. So one of the first questions I should say is, can I use u sub? The answer is no. No. Why? Because the derivative of negative 4x is not equal to whatever's on the outside. You guys see that, right? That's the only way u sub works. Things have to nicely cancel out. Otherwise, you can't use it. So u sub's out the window. The next thing you ask yourself, is there a product of 2 functions? I'm sorry. Yeah, FCN is my shorthand for function. Just giving you guys a heads up. This means function. And you say, oh, look at that. Yes. So then it's going to be use integration by parts. right? And then kind of like a flow chart almost. You guys are in MATLAB and hopefully are familiar with comp sci, right? It's kind of like we're doing like an if then statement, right? So like the next thing we would probably ask ourselves is one of the functions a power and the other an E or a T, right? And it's an exponential function. So like this tells you use tabular method. If the answer to number 2 was no, we would have to pick another method, right? That another method is one that we're going to talk about today is like partial fractions, or you could use trig sub, which I talked about in the video, right? Things like that. So like these should be the thoughts going through your mind as you're doing an integration problem. All right. Please don't just like blindly pick one of the methods and be like, oh, let's hope it works. All right. With every problem given to you guys, there should be a proper method to be used. All right. All right. So here we go. We're going to use tabular method on this one. So we go U, dv, make my column of U's, make my column of dv's. So shout them out. What's my column of U's going to look like? What is my column of U's going to look like?
X cubed, 3x squared, 6x 60.
Mhm. So once again, this will dictate how many dv's I need, right? Make sense? This is going to get real ugly. I came up with this problem off the top of my head, so I apologize if it's going to get super ugly. But here we go. That means my dv by default is going to be e to the negative 4x. And oh boy, we got to integrate these, not derive, integrate, not derive. So what's going to pop out each time?
I think I got negative e to the negative 4x over 4.
Negative e to negative 4x. So I'm going to put a 1/4 in front. Okay. And then?
Yeah. And then 1/16 e to the 4x, or e to the negative 4x.
Good. Who's talking right now, by the way?
Andrew, hi.
Andrew.
Yes.
All right. Go ahead.
Negative 1/64 e to the negative 4x.
Mm-hmm.
And then e to the negative 4x over 256. Or yeah.
And yes, that, oh shoot, what's the, that time playing, oh man, was 2048 like, wait, is it 2048? Yeah, was 2048 like a game you guys played or no?
Yeah. I
Yeah.
played
At
that.
your generation?
Yeah, I
I've
played
never
that.
gotten past
Wow.
2048 though. I've still never gotten past 2048. That's like I get to
Bro, come on, get on that level, man. No, I'm just kidding. Yeah. Anyways, all right, so here we go. Now we do our Zorro method here, right? If the Zorro method is a little too like, it gets a little too messy for you, it's fine. Just think diagonals. If you didn't like Zorro method, it's just you're going at a diagonal, and then signs alternate. We always start with positive, so it goes plus, minus, minus. And it looks like we're gonna have 4 terms in our final answer. So putting it all together, you go term by term, and just please watch out for those negatives, because you know it may have like a double negative, it could have a triple negative depending on the problem, you know, so you just got to watch out for that. All right, silly mistakes are the really, like, those are the things that get people. Those are like the landmines. You just got to watch out. So the first term, it looks like it's going to be x cubed. Oh, watch out for that negative, right? So negative x cubed over 4 e to the negative 4x. Yeah, is that right? Does that look right to you guys? I don't know.
Yeah, that's right.
Someone want to tell me what the next one is?
It's gonna be minus again.
Mm-hmm.
And I got 3x squared over 16 times e to the negative 4x.
I agree. Can someone give me the next one?
Yeah, it's another negative. I think they're all negative for this.
Okay.
I didn't simplify, but I got 6 over 64, or 6x over 64 times e to the negative 4x.
Usually professors want things simplified. So let's
Yeah.
try this thing. What is that? Does 3 go into 64? No. So 2. So 3 and 32. And then the last one. Someone besides, who's this? Andrew?
Yeah.
Someone besides Andrew. Brandon, what you got? Can you give me the last one?
It would be a negative,
Mm-hmm.
and then it would be 6 over 2. What is that? 256
Mm-hmm.
times e to the negative 4x.
Beautiful. And simplify this too. This 3 go into 256.
No, I don't think so.
It's 3/126.
Thank you. And that's it, we're done, right?
Sorry,
Oh,
128.
128.
No, 128. Yeah. My bad.
And plus C.
Ah, I thought no one was
Ah,
gonna say
plus C.
anything. How many of you forgot the plus C? I know some of you forgot the plus C.
Forgot the
Minus
plus C.
2,000 points if that happens to you. I'm not even kidding. Please don't forget your plus C's if it's an indefinite integral. But that's our final answer. It's ugly, I know, but we got there really quick, right? That's how integration by, that's how tabular method works, right? That's why we like tabular method, because it's super fast. Otherwise, we would have had to do this like 3 times with the formula, and it would have gotten real messy, right? I think that's it for integration by parts, though. I think that closes the section out. Anyone have questions on tabular method?
Is this under 7-1?
This is still under 7.1, yeah.
Alright.
So if you guys remember, 7.1 was integration by parts, right? It had those weird cases. 7.2 is on trig, like trig functions being raised to certain powers. There was this page that I think Gina should have referred to in recitation that gave all the reduction formulas. We are not going to do reduction formulas, but they might in the fall. So please just keep that in mind. And then 7.3 was on trig substitution. That was also in the video. So I'm not going to cover that here. All right. So please look into trig substitution. That stuff it's new. It's new for a lot of you. So please look into that. All right. Which brings me to 7, what is it? 5. What the heck is 7.4 on? 7, hold on. That is trig sub is 7.3. 7.4 is, oh yeah, 7.4 is on hyperbolic. It sounds like that's like a DBZ term, but like a hyperbolic and inverse hyperbolic like trig function stuff. That stuff is, I don't think professors cover it. I don't know. When I took it, I don't think my professor went through that. So I'm not even going to talk about that stuff. So I'm just going to jump straight to 7.5, which is something called partial fractions. Here we go. Starting 7.5. Partial fractions. So this is yet another method on how to integrate, right? This has to be another kind of like tool you keep in your tool bag thing, right? For integration. So partial fractions, well, it's kind of in the word. It deals with when you have crazy looking fractions in your integrand. So yeah, so this is the way I usually teach partial fractions. So let me start off with something that you guys hopefully should know, hopefully. Okay. Fractions, I know, you guys don't like fractions, right? That's why a lot of people hate this partial fraction stuff, but I'm gonna start off easy. How would you guys normally do this? If no calculator, like you gotta do this like the old fashioned way. What would you normally do?
I would
Multiply.
get a common denominator.
Common
Yeah.
denominator, right? You gotta multiply the top and the bottom by the same thing, yada, 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 right? I'm just gonna dot. Okay, I'm not even gonna go through that. So you guys should know how to do that one. But then when you guys move to algebra, you guys dealt with problems that were a little bit more complex, but the idea was exactly the same, right? You dealt with polynomial fractions and adding them and subtracting and things like that, right? How would you do this one? We're actually gonna do this one. So how would you do this one? Yeah.
Multiply the first one by x plus 4 over x plus 4, right?
Mm-hmm. And then the second
And,
one by
x plus 3 over x plus 3.
Exactly, right? You would simplify this, you get x plus 4 on top minus, and don't forget to distribute the negative on top. I'm gonna leave it as x plus 3 times x plus 4 just on the bottom for the class's sake, because it deals with the lesson. But on top, right, you would get you'd simplify, the x's would cancel out, and you're left with 1 over x plus 3 times x plus 4. Right? Oh man, partial fractions is easy. Okay, no, this isn't the partial fractions part. Partial fractions is essentially this what we just did, but in reverse. So instead of having 2 fractions and combining them into like one term, you're starting with the one term and you're trying to figure out what the components are that made up that term. Do you guys see what I'm saying here?
Yeah.
Right. So instead of going from here to here, we're talking mainly about going from the red direction, starting from some simplified fraction and then breaking it down into two expressions. Yeah, so let's see here. If I have, I'll call this example 1. If I have 7x minus 13 over x squared minus 2x minus 3. Yeah, I just cranked it up on you, right? I know. Let's say this is my fraction, and I want to know what this is going to break down into. Where should we start?
We should start with the denominator, right? And factor it out.
Who's talking right now? Who's speaking right now?
This is Jeremy.
This is Jeremy? Oh my gosh, Jeremy. Yeah, absolutely. Freaking killing it, dude. Yeah. We need to break down the why did Jeremy say to break down denominator? Why not the numerator? Why not something else? Why is he saying go for the denominator first?
Because then you can find out if there's something you get to multiply to get the, I don't know how I'm trying to say it, but like,
It's a polynomial.
It's a polynomial, okay, or with the assist. So that means
You could
You
figure
can
out
find
what
what
the original fraction was. So what
yeah, you can figure out what the original denominators were if you know if the denominator is factorable, right? If the denominator is factorable and you figure out what those two components are, then you know that this thing had to have come from those said two components. So let's figure that out first, right? Let's factor this thing. What are we going to get when we, oh gosh, do you guys remember how to factor? It's an algebra thing.
yeah.
x plus 1, x minus 3, right?
I don't
Yeah.
know. I hope so. Let's see here. X, 1 times negative 3, okay, and then you got a positive 1x and then negative 3x to get the negative 2x. Yeah, all right, I think we're good. I know, it's been a while since we factored, right? It's very important though that you know how to do that though. But yes, so what does this mean? This means this fraction came from two other fractions being added to each other. The reason why I'm using a and b is because we don't know what the numerators are. So I'm just kind of putting a variable in as placeholders. But we do know what the denominators are, right? This one, I'm going to say is x plus 1, and the other one, x minus 3. Does order matter? Should I have put the x minus 3 first and the x plus 1 second? What do you guys think?
I don't think order matters.
Why not?
You're adding them.
It's addition, yeah.
It's addition, right? It's commutative. So it doesn't really matter. I think the most important thing to watch out for is just make sure your variables are consistent. I'm actually going to write that down because that's actually kind of important. Make sure variables are consistent. This is really, really important. Meaning, if the a is over the x plus 1, that means the a has to stay over the x plus 1 throughout your whole problem. If the b is over the x minus 3, that b has to stay over the x minus 3 throughout the whole problem. You can't switch them anytime you want. Does that make sense? All right, please watch out for that because that, that does affect your answer. So here we go. What are we doing again? What I forget. What are we doing here?
Partial something, yeah.
Okay, partial
fraction.
something.
Partial
Partial
fraction.
fractions.
So what's the goal here? What are we trying to do again? What are,
We're
Figure
trying to
out
find
the
out what two
original- oh.
fractions
Gotcha.
mean.
Right. I remember now, right? We started with a fraction and we're breaking it down into two pieces. I know it's really easy to get lost in the math and be like, wait, what am I doing again? Right? It happens all the time. So yes, we're trying to figure out what are the components. So that means we have to figure out A and B. So what this actually turns into is an algebra problem, believe it or not. Because watch, we don't like fractions. I know, right? Fractions suck. So why don't we get rid of them? What can I do to everything here to get rid of all the fractions so there's no fractions? Ooh, it's and the room fell silent. Not sure. If the problem was like x over 7 is equal to 1 over 14, what would I need to do to both sides to get rid of the fraction?
Cross
By the
multiply.
reciprocal?
Not multiply by the reciprocal.
Cross multiply.
It's not, I mean, I guess you could cross multiply, but we don't have two monomials. Well, the other side has like two terms, so we can't cross multiply. I mean, you can, but if you want to combine them, but that we don't want to combine them.
You just multiply both sides by the, what's it called? The GCD? Is that the right term?
No, not even close,
No?
but I know what you're trying to say. You,
The big denominator
the big boy, yes.
that is common,
The
not the
least-
greatest common
The
denominator.
least common denominator, that's what it's called, right? I know, these words that you guys probably haven't heard since like elementary school. But yes, you gotta multiply both sides by the LCD, the least common denominator. And what is the least common denominator? It's this guy right here. If I multiply everything by x plus 1 times x plus 3, right? Because it's an equation, I gotta do it to both sides, so I do this, right? Watch what happens. What's left on the left side?
7x minus 13.
Yeah, the denominator goes away. The right side, interestingly enough, the denominators will cancel out and you're basically left with like the other factor, if that makes sense, right? So if it's like a over x plus 1, you're left with a times x minus 3. Sorry, that should be a minus. Minus 3. I don't know why I did that. X minus 3. Do you guys see that? Does anyone need me to go through that a little bit more in depth or no? Make sense? That means the other one's going to be b times x plus 1 because the x minus 3 is canceled out. All right, so we got rid of the denominators because we don't like fractions, right? Whatever. But, oh man, how do I solve this thing now? Kind of tricky looking, right? I'll tell you this. What this is, it's actually a system of equations, believe it or not. I know you guys are used to seeing system equations like two things stacked on top of each other, you eliminate or substitute or whatever, right? But this is actually a system of equations. You have two unknowns, a and b. X can be any number of ones, if you think about it. As long as I plug in the same number for x each time, I can plug in anything for x. I can plug in 0 for x, 12 for x, 100 for x, and this equation will stay the same. Do you guys believe me? Yes?
Yeah.
So,
I believe you.
thank you. So what we have to do here is what I like to say, pick smart values for x. Anyone see what I'm trying to say here?
Yeah. So it got to be like 2 or something like that, right?
Right, but we don't want to just pick any x. We don't want to just pick like, all right, plug in like 100. What's a smart value of x to plug in that will eliminate one of the variables?
3.
3 or negative 1.
So
You guys see that?
or-
Negative 1,
yeah.
right?
This
If you're
is how you
looking for the
determine
zeros.
your smart values of x. Make sense? So I'm going to let x equal 3 to start because that's going to kill the a, and then I can solve for b, right? And then on the other one, I'm going to let x equal negative 1. That's going to kill the b, and then you can solve for a. You guys see how we're doing this?
Yeah.
Pretty cool, right? I know. So if I let x equal 3, let's see on the left side, that's 21 minus 13. What is that, 8?
Yeah.
On the right side, the first term dies. The second term becomes 4b. And look at that. Oh, snap. We just solved for b. It's 2. Pretty cool, right? I know.
Yeah,
I
that's
know. All
so
right, let's go. All right. And then when we let x equal negative 1, what is that? Negative 7 minus 13. That's negative 20. The second term dies, and you're left with negative 4 times a. So a is equal to 5. That's the right 4. Anyone lost so far? Am I going too fast? We good? All right. What are we doing again? I forget. What are we
Trying to figure out
trying
the
to find
original
out.
fractions.
Okay, so what should I do from here now?
Just substitute
Yeah.
them and
Yeah,
back
let's just
in.
plug them in and see what happens, right? So b is, so this is what I was saying before, right? Make sure your variables are consistent. You can't plug 2 in for the first one and then 5 for the second one. It's not going to work. You're going to get the wrong answer. All right. So please make sure your variables are consistent here. B is 2, so it looks like it's going to be 2 over x minus 3. A is 5 over x plus 1. This is all equal to our original expression, right? So it's going to be 7x minus 13 over x minus 3, x plus 1. And we did it. What did we just do? We broke down, we decomposed a fraction. We used partial fractions to decompose a rational expression. A lot of words in there, I know. But we just pretty much broke it down into its components. Anyone have questions on this?
So that's the end. That's the answer right there.
Yes, I'm glad someone asked that. What's the point of this? Why are we doing this? Was there no
So we
point?
can break down a complicated integrand.
We're talking about integrals, guys. We're in chapter 7. We're talking about integrals. So what would happen if I did this? Oh, and now the picture comes into focus. Now we're like, oh, that's why he taught us this. It's because when you have a fraction, I'm sorry, when you have an integrand with a fractional like function, we need to know how to integrate it. We did not know how, we couldn't use u sub on this to start with, because if you let u equal like the denominator, it won't pop out the numerator, right? So we needed to decompose this into this form, because we actually do know how to integrate this, believe it or not. Do you guys remember how to integrate when x is to the power of 1 in the denominator?
John, I don't know if Mohammed's in the waiting room, but he asked if he could be let back in. So I'm assuming he must be.
Oh, Poopy, what happened?
Said his Zoom crashed.
Oh, his Zoom crashed? Oh, shoot. Thank you. Guys, please interrupt me ASAP when that happens. I didn't see that on my fault. Mo, you back in? You all right? Everything
Yeah,
okay?
crashed for some reason.
Okay.
Oh,
All right. Okay. What was I saying? Oh, how do we integrate stuff with x, like x to the first power in the denominator? What comes to mind? What should come to mind?
Should we move it up to the numerator?
Mm,
U sub.
Come on, guys. What's the integral of 1/x?
du
Is
over u.
Oh,
Natural log.
my heart, mi corazón.
Is it
it's just to
the
the negative
integral
power, right?
-1 x negative first power?
What, when you derive it, gives you 1/x?
Natural log.
ln
ln, natural
Oh.
log, guys. It's ln of, more specifically, absolute value of x. You guys remember that? You guys remember ln? My good friend Ellen? No? No, guess not. Oh, geez. Guys, please, you have to know your integral rules. This is what I was saying in the day one. You have to know your derivative integral rules backwards, forwards, and all around. So please make sure you know them. That means since these are to the power of 1 as well, these denominators, these are actually going to become ln as well. Just don't forget, watch out for constant. I'll write that down. Watch out for constants, because like you have to undo the constants, right? Watch out for constants. And don't forget absolute value sign. All right. So putting this all together, this becomes 5 ln absolute value of x plus 1 plus 2 ln absolute value of x minus 3. And we can't forget about our trusty plus c. That's it. This is partial fractions. Mic drop.
All right, makes sense.
You guys like that, right? You guys like how I didn't talk about integrals at all first? I was just talking about,
Yeah, that was great.
and then I put in the integral part. Yo, it's so cool. I love it. All right. Woo. Any questions? This is essentially partial fractions. There are other weird cases that I'm not going to talk about because I can't. Anyone want to guess what the other weird case would be? No. I'm just gonna say it because there's no time. You guys realize the degree on the denominator was 2, right? And there was 2 factors. Well, what happens when
If
there
it's
are,
not, if it's
there are
more
3
than 2,
factors? What happens when there's 4 factors? When there's 5 factors? What happens when the degrees are the same? What happens when the degree on top is bigger? Those are the other cases that I unfortunately usually go through, but just for time's purposes, I can't. So for the homeworks and the quiz and stuff like that, really you should probably expect to see like degree 2 stuff. Okay, so that's like your, I guess, gift or whatever. But those other cases are pretty interesting. If you want to check them out, they're in the book. By the way, we're in section 7.5, which is around this is page 442 in the PDF that I sent you guys. So if you guys want to check out those other cases, they're there if you want. All right, let's mosey on to oh my gosh, 9 minutes. Let's mosey on to 7.6, which talks about improper integrals. No, I'm sorry. Sorry. I got a plug here. Section 7.6, it's kind of like it's like a compilation of all integration techniques. In fact, I'm pretty sure Gina's gonna assign you guys a bunch of problems from this section because it's basically they throw an integral at you and you have to figure out what method do I use, how, like, what's the best way to do this, and yada yada yada. I highly recommend you look through 7.6. They talk about strategies on choosing which like method to do and all that jazz. So please, if you get a chance, look at 7.6. I'm gonna ask you to go through some problems with you guys in recitation as well on Tuesday. All right. So 7.6, it's just all the methods covered so far, all the methods that you're going to see in Calc 2, essentially. All right. So, and then 7.7, I'm just going to talk about this real quick. It's talking about improper integrals. Oops, integrals. All right, you guys ready? Here we go. Improper integrals. Well, what the heck is an improper integral? Does that mean that the ones we've been doing were proper integrals? What makes an integral improper, and why do we care about it? Well, let's talk about it. Improper integrals, I guess to kind of sum it up real quickly, it's basically a definite integral. You guys know what a definite integral is, right? I think we talked about this a little bit. It's a definite integral, meaning an integral with bounds. But one of the bounds either goes to infinity or goes through an infinite, a vertical asymptote. Sorry, that's what I'm going to say. Goes through a vertical asymptote. It basically, I don't know if breaks the laws of math, kind of like, I feel like that's like an exaggeration, but I feel like you guys would retain it better that way. But it kind of like, it goes where no man has gone before, So like, so for example, if I have, oh my gosh, sorry, I had too much coffee today. There we go. Let's say I had the function e to the negative x, right? And let's say for funsies, I wanted to figure out, well, what is, wait, e to the negative 1, that's, yeah, okay, that would be somewhere there. So what is the area under the curve from 1 all the way out to infinity? Whoa, right? You guys have only played with finite bounds in your definite integrals, right? That's what kind of makes this thing an improper, quote unquote, integral. It's because you're going to either mess with the domain restrictions or you're going out to an infinite value. So we need kind of like an extra step. So the catch with improper integrals, everything is the same. Everything is exactly the same. The only catch is you need to deal with this infinity like type of stuff playing around, messing around in our bounds. So if I were to set this up as a regular integral, I said, I want to know what the area of the curve is from 1 to infinity of e to the negative x. Right? Anyone have questions on the setup, why I set it up the way I did? No? All right. So so how do I do this? How does this work out? I have an infinity in my bounds. I can't go to infinity. In math, okay, not physics. In math, infinity is undefined. It's like, it's not a like real answer. You can't quantify it. In physics, you can. They do it all the time, and it pisses the mathematicians off. I don't know if you guys know this. There's like math and physicists are like brothers, but like we kind of hate each other, because they kind of do stuff that pisses us off. We do stuff that pisses them off. So yeah, just letting you guys know. So what do we need to do? How do we go about doing this? Well, we need to put in a placeholder for that infinity. And what we're going to do is actually bring in a tool that you guys probably haven't used in a while. We're actually going to use limits to turn that infinity into something that we can actually like compute with. So what I'm trying to say is we're going to let some placeholder, I'm going to call it R because I think most books use R. I'm going to let I'm going to let R go to infinity. And in doing this, you are actually allowed to now compute this integral. Because watch, we know how to play with integrals. We know how to play with limits. So all we're doing is just putting them together. So watch what happens. What is the integral of e to the negative x? I just saw a huge ass spider just walk on my wall and now it's gone. Oh god. Sorry, go ahead. What is the integral of e to the negative x?
Negative e to the x.
Good. Negative e to the what?
Sorry, negative x.
There you go. All right. So we anti-derived it. Our bounds are going from 1 to r, and we cannot forget about that limit sign. Wait, John, so does this mean I have to put that limit as r goes to infinity on every single, yeah, you have to put it on every single step. Okay, please don't, oh God, I see this so many times when people like do this and they're like, what, I wrote the integral. I'm like, no, you left out the dx, or like you left out the bound. Don't get lazy, guys, please. Don't get lazy with your work. It's a big no-no, all right? So yes, make sure you write the limit on every single step, all right? And then from here, like I said, it's exactly the same. You just do upper minus lower with the limit at the very end, okay? You basically deal with the limit at the very end. So you're pretty much gonna have a limit on every single one of your steps. So we go negative e to the negative r minus negative e to the negative 1. And I guess technically the limit is going to everything, but it only affects the stuff with r in it, right? So it's really only affecting that first term. So that first term, if I were to rewrite it, becomes negative 1 over e to the r. And I'm letting r go to infinity. What happens to this first term?
Turns to 0.
It turns to 0, right? As r gets bigger and bigger and bigger, that fraction goes to 0. And that's what limits let us do, right? So this whole thing actually just goes to 0. And oh my gosh, you're left with 1 over e. No fanfare, no like, oh, really? I have to teach you guys when to say that too. Do you guys not see the impact of what, do you guys understand what we just did here? No, okay, I'll explain it. I'll go back to the picture, watch. Look at the picture. We let an area go unbounded. We let it go off to infinity forever and ever and ever. And somehow we ended up with a finite value. Does that not blow your minds?
It blew my mind in the middle of the work where I realized where it was going.
Okay, all right, fine. Well, I mean, you didn't like say anything though, Dan. Where's the shout out? Where's the props for that, dude? Gosh, you guys.
I think a
not
lot of
see
people
that?
feel silly to unmute to say oh when they say oh.
No, come on, man. I need
Yeah, honestly,
that. That
reading
is
the
my like.
feels a little weird. It's like
As a
oh,
teacher, that's like my drug. I need to hear that from like the students, like that. Oh, that's cool. You know, dang, man.
it probably wouldn't be as bad if we were in person.
All right. My BPM's going up a little bit. All right, so here we go. What does that mean? That means there can be times when the answer is not a finite value. Makes sense, right? If we're going off to infinity, or if we're dealing with like infinity, then of course there are going to be cases where the area is going to be infinity, or like just not a finite answer. So they use special words for this. Okay, you don't actually have to say this if your answer is a finite value, but they use the word convergent. That tells you that you get a finite value. If you get like infinity, sorry, oh my gosh, so I'm rushing because of time. If you get infinity or like negative infinity, oh my gosh, negative infinity, or like a sort of like a D&E type of thing, right? We call this a divergent answer. So let's say in the work, you ended up with infinity because as you let R go to infinity, it blew up to infinity. Then you would say the area diverges, or it diverges, or divergent answer, whatever, however you want to say it. But these words we're going to be using a lot actually, especially with the series stuff later on. So I just want to expose to you guys now with this. All right. That was really fast. That was improper integrals in a nutshell. There's like one other weird case I'm probably gonna ask Gina to go through with you guys. That's at like it's like at an asymptote. So it's like, let's say I have like a function that looks like this. right? It's a rational function. And let's say I wanted to calculate the area from here to here. This is improper because those asymptotes, where do they go? To infinity. So there's a special trick to deal with this as well. So I'm gonna ask Gina to go through an example like that with you guys too, right? But this is essentially like the heart and soul of improper integrals. It's basically when you deal with areas that kind of are unbounded or like they go to infinity and things like that. All right. Do we have any last minute questions before I let you guys go? I think that's it for today.
Are you gonna explain that further in the video?
Well, explain what further?
Improper integrals.
Right. So I'm gonna ask Gina to go through
In the
other,
recitation.
other weird cases in recitation as well. All right. But I think that's it. We pretty much through chapter 7 already, which is nuts. Next class, we're going to talk about differential equations a little bit, something called logistic growth, which some of you may know. And then after that, we start series or sequences in series right away. So yeah, be ready for it. Sorry to keep you guys extra, but guys, if you have questions, please reach out. Let me know. All right, and yeah, have a nice weekend. I'll see you guys on Wednesday.
Have a good one.
Thank you. Take
There we
care.
go.
Goodbye, you too.
Bye bye.